Okay, this is part 5 of the Hearst Amateur Radio Club General License Upgrade class they gave in October of 2019. Be sure to check the playlist here for all the videos in order. This is part 5. Take a look, and I hope you enjoy it.
Shut up and sit down.
We're going to talk about now what's inside the radio. We're going to keep it simple. We're going to talk about little blocks. We're not going to talk about the components themselves right now. We're going to talk about functional blocks and of a simplified single sideband transmitter. So we start out and we're going from left to right. Left is the microphone. That's where you talk. That microphone's job is to change. Microphone's job is to change audio frequency into electrical frequency, an analog electrical frequency. It converts voice signals to electrical signals. They're very low value. So you go in, next thing you go into is a microphone amp. That mic amp amplifies the signals. So it's sort of loud enough that the rest of your signal can use it. Then it goes into the balanced modulator. Okay. The balanced modulator, remember the last Tuesday when we talked about a single sideband signal, where you had a single RF signal called your carrier. That was the radio frequency signal. And you combined that radio frequency signal with an audio frequency signal. Well, here's the radio frequency signal. The oscillator generates the radio frequency signal. And the balanced modulator combines it with the microphone amp, the audio signal, and now you've got a double sideband AM signal. And now you've got a double sideband AM signal. Now you're going in here. So out of here, you get the carrier frequency. You get this plus the sum of the audio frequency and minus the audio frequency. So you've got the carrier, the upper sideband, and the lower sideband. That's what comes out of the balanced modulator. How do you get rid of them? You go into a crystal filter. The crystal filter's job is, it's very narrow. The crystal filter's job is to filter out and allow only one of those sidebands to pass through. It takes the RF signal out, and it takes either the lower or the upper sideband signal out. That's where we decide on the radio, if we're going to transmit, which one we're going to use, in that section right there. Now, it's still not low enough. It's still in microvolts. You can't, it won't transmit. So it goes into the IF amp, which increases the signal. And then it goes into the RF amp. The IF amp's kind of an intermediate type thing. If you try this really low level signal into the RF amplifier, it's going to kind of overload. It's going to kind of load the RF amplifier down. So you increase it enough so that it's usable by the RF amplifier. The RF amplifier is the one that takes, on my radio, the one that takes that microvolt signal and amplifies it to 100 watts. And I hook that up to the antenna and I radiate that wave out into space. That's how it works. Is that simple? It makes sense. Did you recognize things we've talked about so far? We talked about the RF amp, which runs the ALC. We talked about how a single sideband AM signal is generated, what a single sideband signal looks like. The IF amp makes it stronger. The RF amp makes it stronger, even stronger yet. And we radiate out the antenna. That's a very simplified block diagram of a single sideband transmitter. Now let's look at a couple parts on that we haven't talked about. The MyCamp. The MyCamp, that amplifies the signal from the microphone. That's also called a speech processor. It increases the intelligibility of the transmitted phone signal. The advantage of it is you can increase the average power by increasing that. During poor band conditions, you can crank that up a little bit and maybe make your voice signal a little more robust. But there's a limit to that. If you crank it up too far, you get overmodulation. You exceed the ability of this amplifier. You exceed its design, you exceed its components, and you get overmodulation. That gives you splatter, which is spurious stuff on the outside. It causes distorted speech. It causes excessive bandwidth. Makes your bandwidth wider than 2.8 or 3 kilohertz wide. And it picks up a lot of background noise. The more you amplify that noise, the more everything in the room around you gets amplified as well. Yeah.
To listen to some of these nets, what is it when they sentence, but then it cuts out in one word and then it cuts back on. Are they using box or something? Or?
I guess I don't,
It happens all the time for us.
it may, which kind of net you talking about?
Just the regular scheduled ones in the area.
Every once in a while, it may be interference. We have some folks in the area who aren't quite playing with a full deck, and they take great pleasure in interfering with other stations. And all it takes is somebody to just punch the mic button, let it back up.
It's like it electronically disconnects
just
one word.
Yeah, it covers up. Sometimes it's just their radio.
I mean, how would you, could it be?
You just tell them they're breaking up. So if they're using a handy talkie, in a lot of cases their battery's getting low. But in some cases they're not holding the mic button down. In some cases it may be a defect in the radio. But if they were over modulating, if they're MyCamp, if they were over modulating, you may hear that if you ever listen to Citizens Band, there are some Citizens Band signals that are horrible. You can hardly understand them. There's echo in the background. You can hardly understand what they're saying. Well, they've got their mic gain. They've had their radio modified where they can crank their mic gain up because they think they're getting more power. They're getting out better. And actually all they're doing is interfering with other stations and making it hard to hear what they're saying. And I'm not down on CBers. The problem is there's too much erroneous information going around out there, and too many people who are willing to put a screwdriver in their radio to fix it and make it talk better, and they do not train to know any better because they're not required to be trained. You could open up your radio and play inside of it all you want. It's not legal for you to open up the inside of your CB radio and play it. To modify it other than how it was designed. You can do whatever you want. Now, it doesn't mean that you're doing the right thing, but that's why there's doors on top of a lot of the old radios used to have a little door on top. You could reach inside and change coils and make adjustments and do all sorts of stuff. The MyCamp is good. It helps you increase your average power. It helps you increase the robustness of your audio signal. You want to use it with caution. You want to use it till it sounds good. You may want to tailor your voice to increase. Sometimes you can use it to tailor your voice to increase the treble or increase the bass, whichever way work. That's all fine and good. Just be careful not to overdrive it. Don't drive it up past what its limits are, what it's been designed for, because you're going to get distortion and splatter. They're going to take up too much bandwidth.
Times you wouldn't know it unless somebody tells you, would you?
You will look. Remember we talked about the automated level control? Automated level control, when and you can see it on a meter. If you're going to do that, turn your automated level control over, and it'll show you how far you're transmitting. I mean, what your audio signal looks like. It'll show you. If you're starting to peak the end of the automatic level control on peaks of your voice, you're too high. Turn it back down. Use that automatic level control meter on your radio to do that. But most of your radios will tell you what's an average setting. They'll come with an average setting, which is not bad. The other part, the RF amp, that amplifies the RF signal for transmission. There's several different designs of amplifier. And there's designs of amplifier are typically called Class A, Class AB, Class B, and Class C. And they're designed and built different ways for different applications. Now, we look at efficiency. Class A is 100% linear. It exactly duplicates the signal that goes in. The signal that goes in is exactly duplicated when it goes out. It's just at a higher power. There's no distortion. A Class A amplifier is best amplifier for AM, amplitude modulation, and single sideband. There's also a Class A, but it's the least efficient. It uses the most power. The ratio of how much power going in to how much power going out is the highest is the worst ratio, put it that way, the highest ratio. There's a Class AB. It's about 75% linear. It's suitable for AM and FM and single sideband. The advantage of that is it's more efficient. It doesn't use quite as much power to get the same power out as the Class A amplifier does. So, but typically for voice communications, that's not bad. If you're not playing music, which we're not going to do, you really don't care what your wide range is. You just want to be understandable. You want to be crisp and distinct and understandable. And 75% linear is probably pretty good. So what you're going to do is you're going to take less power in to get the same power out with a Class AB. Class C amplifier is only about 50% linear. Now that's okay for FM. The way FM works is fine for FM. So that's good, but it uses less power. Class C is the lowest linearity. Now it's excellent for CW, it's excellent for Morse code because it's transmitting nothing except a carrier. There's no information with it, so all you've got is carrier, so it's great. Lowest efficiency is Class A, highest efficiency is Class B. And when we say efficiency, it's because it uses less power in for less power out. We talk about how we talked about efficiency is expressed as the RF output power divided by the DC input power. For example, 50 watts RF out, 125 watts DC in. Remember, we're talking about DC, we're talking about and RF, is a 40% efficiency. So I put 125 watts of DC current in there, and I get 50 watts of RF energy out. Got on a 40% efficient RF amp. In an RF amplifier with tubes, now a lot of RF amplifiers, the stuff that you're using, all your radios have one. Your 2-meter radio, your handheld radio has an RF amp in it. It puts out 5 watts or 7 watts, something like that. Your mobile radio has an RF amp in it. It puts out 45, 50 watts. Your HF radio is going to have an RF amp in it, probably put out 100 watts. Some of them put out 200 watts. If you add an amplifier on the end, it may not be solid state, depending on if you want to run 1,500 watts on it. You may be running a tube amplifier in that case. You need to neutralize the tubes to prevent self-oscillations. And we'll talk about neutralization in the extra class. You won't have to know. All you have to know is that you may need to neutralize your tubes to prevent self-oscillation.
Do they still use the tube amplifiers?
Pardon?
Do they still use the amplifier tubes?
Oh yeah, yeah. They do. You're not going to find them in you're going to find them in standalone amplifiers now. Your Kenwood TS520, your Yaesu 101, FT101. Those were older radios. They still had they had amplifier tubes in the output. Everything else was solid state, but they had amplifier tubes in the output. Because at that point, when they came out 25, 30, 35 years ago, time's getting away from me now, there just wasn't suitable, affordable solid state amplifier transistors out there at the time. But we're going to talk about those vacuum tube RF amplifiers. If you've got one, if you want to start running 100, 1,500 watts, even 500 watts or 600 watts or 1,000 watts, you'll probably be using one of those. And it's kind of a brief introduction on how you tune one up. The nice thing about solid state, the newer solid state HF transceivers is they're solid state all the way through, and you don't have to tune up the amplifier. You just switch the band switch, and it has the amplifier, the solid state amplifier, tuned up the way it needs to be tuned up. So you don't have to do that. However, if you're using an older one or you're using a vacuum tube, you're going to need to tune up that amplifier based on when you change frequency, you're going to have to retune your amplifier. So when you tune an amplifier, the first thing you want to do is you want to adjust the plate loading. And we're going to talk about plate a little bit later. We're going to talk about plates and grids and all that sort of stuff in just a few slides down the line. But you want to adjust the plate loading control for maximum power output without exceeding the allowable plate current. And the manual will tell you what the maximum plate current is that this radio will handle. So you, on the frequency you're on, you set it to the frequency you're on, and you adjust that control until the meter shows you the maximum power output that you can use without exceeding the allowable plate current. Now you've got maximum power. And then you have to tune the thing, you have to call dip the amplifier. Then you adjust the plate tuning. This is for the frequency. You adjust the plate tuning for a pronounced dip in the plate current meter reading. Okay, that means it's most efficient. It's out there in its most efficient spot. So you load the plate, maximum loading, and then dip. Load and then dip. Care and feeding of those things. You got to be nice to them. That automatic level control, we talk about how high you turn it up. Well, you want to turn it up so that you prevent excessive drive to power to the amplifier. It not only reduces signal distortion, if you've already got distortion, the last thing you want to do is amplify it, that for a 100-watt radio, is amplify that distortion 10 or 15-fold. The distortion you have at 100 watts is going to be greater than the distortion you have at 1,500 watts is going to be greater than what you have at 100 watts. So don't amplify that. You don't want a distorted signal going into your amplifier.
So are they amplifying it for more distance, or?
Yeah, typically what they're amplifying it to have a louder signal on the other end. I can get into the.
Louder, not necessarily distance.
That's correct. That's correct. I've worked offshore stations, and I've talked to offshore stations, and I talk to them, and I run with my 100 watts, and they say I've got a good signal. There's someone else will come in with 1,000 watts, and they've got a better signal. They've got a louder signal, but I've got a perfectly readable signal. They just managed, they managed to kind of override anybody else that's out there. In the case when you're listening to the band and a lot of signals are really weak, well, it helps sometimes to have extra power because it brings the level up. So your signal that would normally be.
Kind of like on a CV that's using a linear or something. They're just they're above everybody else.
They're above everybody, but they're not going any farther. Their radio wave itself is not propagating any farther.
Right.
They're just propagating louder.
But on hand, since they're not all talking at the same time.
No. Yeah. So it's going to be like, it is useful when band conditions, when signal levels in the band are low, it's useful to put a louder signal on. And we can talk about, well, I won't want to get too far off the subject. If I don't have a very good antenna, I don't care how loud your signal is, I'm going to have a hard time hearing you. If I have an antenna that has more gain, it uses my power more efficiently in the direction I want to do, it's just as good as an antenna. If I got a bad antenna and a lot of power, sometimes it's no better than a good antenna and a low power. It just depends. Now, if you got a good antenna and a lot of power, then you're running with the pack. I mean, your signal's going to be heard above everybody else. So it's a personal preference type thing. It's a personal operating preference whether you want to run more power or not. But excessive drive. Solid-state amplifiers don't like excessive drive. They don't like nasty signals going into them. So you could damage those. So the moral of the story is, again, we've talked about excessive drive and excessive drive. Don't crank that automatic level control up. Don't crank that mic gain so high that you've got a bad signal. Because not only sounds bad, it could also damage your equipment, and it causes you to overmodulate. It causes you to use more bandwidth. And if you've got your signal, if you're trying to talk to somebody, and let's say you're working a contest, or you're trying to pick up a rare station that's on an island that's only going to be there for operating for a week, if you turn your gain up real high and transmit a really bad signal, odds are good they won't answer you. They'll answer somebody else. Nasty signals sometimes offend the people on the other end. Alternating current waveforms. You've talked about alternating current when we were back in the technician class. And alternating current is current that changes direction from positive to negative as time goes on. In this chart, height is amplitude or strength. Left to right is time. So you have an alternating current waveform. Now, when we look at alternating current, the top and the bottom of that current is called peak to peak because you're measuring from the peak of that waveform from the bottom to the top, peak to peak. Does that make sense? See on the left side, peak to peak. Okay. However, there's also, if you measure off the neutral point, one side is called peak. You either got peak or peak to peak. There's also now, but that is not, if you're measuring on typically on a voltmeter, if you're measuring voltage, you're measuring 12 volts AC. If you're measuring 12 volts AC, you're typically not measuring the peak. You're measuring what's called the RMS voltage. RMS means root mean square. RMS voltage, you're measuring that. It's the equivalent voltage if it was DC. Notice you got a lot of power down in here. Got a lot of energy in this part of the waveform and not much in the peak. So it's kind of the, almost, not quite the average of that, but it's 0.707. So if that's a 1 volt peak to peak signal, and I measure that, it's equivalent to a 0.707 volt signal. That's called RMS. Volts peak is peak to peak divided by 2. To get you get RMS voltage, you take the peak voltage, not the peak to peak, the peak voltage times 0.7, and that gives you the equivalent of the DC voltage. That's the same amount of voltage. The DC equivalent voltage is the same amount of voltage that it would heat up a resistor, a DC resistor. So a DC equivalent of 200 volts peak to peak waveform is 200 divided by 2, which gives you the peak, times 707, which is 70.7 volts.
Is that the same thing on the root mean square? Is that the same thing as the 3 times square root?
That's what?
Back on that equation before where it says the RMS
Mhm.
and that the root means square. Is that the same thing as square root?
No, it's different.
Oh.
Yeah, that's different. It has a relationship to the square root. It's actually a trigonometric function.
Yeah, 'cause I'm pretty sure that 0.707 comes from a sine.
That's right.
Or, yeah.
Yeah, it's a trigonometric function. We'll get into that more, and unfortunately, we'll get into that kind of stuff more when we do an extra class. So what that is that when I talk about equivalent DC, it's if I had a, the equivalent DC is the same, the voltage it takes to heat a resistor, the same as it would to heat, as DC would heat it. In other words, if I was going to have a resistor and I was going to produce a watt of heat in the 1 watt of heat in the resistor, or I'll just make it use this thing. If I had a resistor and I wanted to produce 7.7 of a watt, 7/10 of a watt of heating, I would need 1 volt peak AC signal. That's the AC signal that heats the equivalent DC. So in other words, if I had a heating element in a stove or heating element to heat up a crystal, the 0.7 watts or 0.7 watts, I would need 1 volt to do that. Whereas if it was a resistor, I would need, it was DC, I'd only need 0.7 tenths. That's the equivalent for DC, because AC is not on all the time. DC is. About some equipment. Nice popular piece of equipment is an oscilloscope. It's a nice thing to have in your shack. It's a nice piece of test equipment if you're going to work on stuff. It shows you a lot of stuff. Oscilloscope, you can look at complex waveforms. I just see that in a single sideband. You can hook it up through an attenuator to your transmitter. You don't want to transmit directly into it because it's a very sensitive device. You don't want to put 100 watts in it. You want to put something in there that'll get that down to microvolts or stuff. But you can look at the shape of the waveform. And oscilloscopes, if you ever watch science fiction movies, even the old ones, they always like to show you sine waves and stuff going across. That was an oscilloscope. This is a multiple trace oscilloscope. This one here will show several different traces at the same time. The horizontal is time. Time goes this way, just like your waveform does. Amplitude goes this way. You can look, so you got a single sideband signal. You want to see how your signal looks. You want to see if it's linear. You can use a 2-tone test generator into the mic on your radio, which is 2 non-harmonically related tones, into your radio, and you can look at and see how linear your device, your amplifier is. You can look at waveforms. You may be looking at AC, think you're looking at AC, pure AC, and you might not be looking at pure AC. You may be looking at some odd AC waveform. You can look and see what your modulation envelope of your radio looks like. You can do a lot of things with the oscilloscope. Nice device. We talked about amplitude modulation. Hopefully you understand what amplitude modulation actually looks like. Amplitude modulation is modulation that changes with signal strength. The lower your voice for a modulated signal, the lower your voice, the less high the waveform is going to be. This is a lower voice. This is one a higher voice, peak in your voice. So an amplitude modulation signal, as it's modulated along, is changing like this all the time. Even though it's made up of a bunch of components, the overall shape is what's known as the modulation envelope. The overall shape of that thing is known as the modulation envelope. The changes are instantaneous with amplitude of the RF wave. The overall shape is the modulation envelope. Time going this way, strength going that way. The peak envelope power, we've talked about PEP a lot of times. Peak envelope power is the highest one. Whatever that shape looks like, the peak envelope power is the highest peak. When you talk at a single sideband signal, the one thing you need to understand, and a lot of people, I've had people go, oh, my radio's broke. I turn my radio on, I put a watt meter on the end of my radio to measure my power output. I pushed the transmit button and nothing happened. The meter didn't go anywhere. Well, did you talk in it? No. Well, you're on single sideband, you've got no carrier. There's nothing there. You have to talk in it first. You have to provide a signal. On an AM signal or an FM signal, if you hooked it up to your 2-meter radio and you pressed the mic button on that, you'd get a reading. You'd get 25 watts. And if you talked it would stay 25 watts. But on single sideband, on AM the same way, you'd get a carrier out of that. But then when you talked on it, it would modulate a little bit like this. But on a single sideband signal, there's no carrier. There's nothing there except the wave, the audio wave. So you don't talk on it. The only thing you see on a single sideband signal is the audio waveform. And that's why single sideband, when we talk about the power, what's the maximum power you can run on 10 meters as a general? Or 15 meters as a general? Or 20 meters as a general? What's the maximum power that you can run? 1,500 watts, peak to peak. Odds are good, most of the time you're talking, you're not going to see 1,500 watts until those brief times that you shout. You're going to see all sorts of different heights. So as you talk onto your radio with single sideband with a power meter on the end of it to measure your power output, you're going to see that needle go back and forth. But this is your peak envelope power. As long as when you're talking through your amplifier, that doesn't get more than 1,500, you're okay. That's what peak envelope power. That's the envelope, which is the overall shape of that waveform. The peak envelope power is the highest point on it. Frequency modulation, different animal. Time for a drink. Frequency modulation doesn't work by changing the strength of the signal. It doesn't work by increasing and decreasing the strength of the signal. The signal's constant. The power level's constant. That's why when you push the button, it reads 25 watts. It's constant. What it does is when you put intelligence into an FM signal, it actually changes the frequency. It causes the frequency to shift back and forth, lower to higher frequency. Your voice component, instead of making it stronger and weaker, makes the frequency increase and decrease slightly. That's why an FM signal is so wide and reaches up so much of the spectrum, because rather than taking a little piece of spectrum and modulating it this way, it takes a spectrum and modulates it that way. Rather than modulate it like this, it modulates it like that. It makes it wider. It's always going to be peak. There's not going to be a peak to peak. It's always going to be peak. Yeah, go ahead.
Is it like we're looking down on it then, right in this image here? Or?
No, you're looking. This is a waveform. This is time going this way. This is your waveform. As your waveform's coming through, when I talk about that waveform, I'm changing the frequency of that waveform. So it's a lower frequency here because the waveform's farther apart. A higher frequency here. The waveform's closer together, based on the audio that's coming in through my speech amplifier, RF amplifier, my audio frequency amplifier. So essentially, like I say, it causes the frequency. If you're looking at the band path, it causes the band path to go like this rather than like that. Deviation is the maximum difference in modulation relative to the RF carrier. How much it goes back and forth. It's called the deviation. How much it deviates from one point to the other. And how does that affect bandwidth? Well, the way it is, bandwidth is 2 times the deviation, because this is double sideband type thing, plus the audio modulation frequency. So whatever the deviation is, plus the audio modulation frequency, is going to tell me how wide my bandpass signal is going to be. Maximum difference in modulation relative to the RF carrier. Now let's look at a generic, simplified AM and single sideband receiver.
Can you go back to that slide? Can you go back?
Yeah.
On the deviation, the deviation says it's the maximum difference. Does that mean it's going to be the difference of the widest part of where they're away subtracted by the narrowest part?
Yeah, yeah,
Just
yeah,
making sure.
yeah.
I'm trying to get it in my brain.
Yeah, that's it.
Okay.
That's deviation. How much at its narrowest spot to how much at its widest spot is it going? It is. That's the deviation. And bandwidth is 2 times that deviation plus the audio modulation frequency. So if I'm modulating with a particular modulation frequency of 15 kilohertz or 15 hertz or something like that, 300 hertz plus the deviation. So you take the deviations, how much is going back and forth, put the audio on top of it. The deviation is going back and forth. That's why it's 2 times. Deviation only measures one direction. Deviation going back and forth measures 2 times. The 2 times plus the deviation plus the audio modulation frequency gives you the total FM bandwidth. Now they can get pretty wide. They can get 15 kilohertz.
Digital is the same thing, just more compressed?
Yeah. Yeah. Digital. The nice thing about digital is it compresses the bandwidth down. That's one of the real advantages of digital. It doesn't use as much bandwidth. Okay, let's look at a basic block diagram of just a conventional, generic, simplest that you can look at AM or single sideband receiver. And we'll start off over here with the RF amplifier. We got a really, really weak signal coming in captured by my antenna. Actually, I've got thousands of weak signals coming in that antenna at the same time. Anything that antenna can pick up is coming in that antenna right now. And they're all very, very weak. And there's some noise in there too. It goes into an RF amplifier because that's radio frequency energy coming in there. So it goes in the RF amplifier. The RF amplifier increases that signal, increases the strength of those signals. Okay? But I got a bunch of them here now. So I need to start getting some of those out of there. I've got what's called a local oscillator. I take this and I mix it with the local oscillator. And it combines the RF and the local oscillator frequency. My local oscillator frequency is going to be low. These are going to be high coming in here. Remember when I mix frequencies together, I get the 2 original frequencies, I get the sum, and I get the difference. Okay. If I got really high RF frequencies up here, and I mix them with a low frequency signal, I get a low frequency, an even lower frequency signal on that. Where before on radio frequencies, I threw out that low stuff, and I only wanted the ones that were up there with the sum and the difference relative to the carrier. I'm interested now in the low frequency signal. So I can mix this together, and I can get this low frequency signal that starts getting down closer to the audio range. I go through the IF filter. The IF filter filters all but the intermediate frequency, which is that frequency now that's the difference of the signal. So I want that IF frequency to go take out all that stuff that's up in the upper RF frequency that I couldn't hear anyhow, and concentrate getting that audio component back out of there again. It filters out all but that. And that's called the intermediate frequency. And now that's still a really weak frequency. I'm going to amplify it a little bit, and I'm going to put it in the detector. Now, let's talk about that single sideband signal. Remember, I took the carrier out? Okay. I need that carrier to make sense of that signal. So I'm going to mix, called a beat frequency oscillator. I'm going to mix that again here and put the carrier back in, the audio carrier back in there so I can understand it. Because if not, single sideband without a beat frequency oscillator mixed with it sounds like Donald Duck. You can't, it's not intelligible. You've got to put an audio carrier back in there with that so I can receive it. So the product detector separates those out and gives me just takes the audio signal out of that. Takes that audio signal, which is now back voice, down in the range that people can hear, down below where dogs hear, puts it into AF amplifier, audio frequency amplifier, and I can go to my speaker or headphones. So what I'm doing is taking all my frequencies, amplifying them, stripping out of all of them that I don't want, and I can vary this. This one here, I typically vary. I can vary that. That's what my tuning control is. I can vary that so I can select which frequency I want that comes out of the mixer. There's an IF filter, IF amp. I put the carrier back in. I detect the audio signal out of there. I amplify it, and I put it to the speaker or the headphones. Yeah.
The BFO is adding the carrier back, you said?
Yeah.
So,
So I add an audio carrier back.
okay,
Yeah.
like on the old Panasonic,
Yep.
dial
Yep.
radio I used to have, had the BFO switch, which acted like single sideband as far as I knew, but I guess I'm listening without a carrier until I hit that BFO.
Until you hit that BFO. Then you can understand it. It sounded like Donald Duck talking before that. Then you can hear it. Then you can, all of a sudden, it's magic. And also puts a tone, if there's a CW signal coming in, you get a thump, 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 thump. It adds that nice musical tone to the CW signal, too. The simplest, absolutely simplest receiver that you can have is a simple superheterodyne receiver where you don't even amplify the signal coming in. You use the local oscillator in the mixer to select out the one you want, and you use a detector to strip out everything except the audio. That's the simplest, not much more than a crystal radio, but it will receive. It's not very sensitive, and it's not at all selective. You're going to be hearing lots of signals at the same time. You're going to have to kind of pick them out with your ears. And audio output usually goes into really high impedance headphones because there's no amplifier in it. It's the next closest thing to a crystal radio. It'd be a transistor equivalent of a crystal radio. Here's a simplified FM receiver. Looks kind of familiar. RF amp, mixer, and local oscillator. They do the same thing. They don't care what kind of signal's coming in. The antenna can't separate the signals, so it's going to amplify everything that's coming in. It goes in the IF filter just like it did before. You've got all the RF stuff out of it now, and you filter out everything except the stuff that's closer to the audio frequency. It goes into a limiter. A limiter's job is to keep the signal going like this, not like that. So a limiter keeps the signal from being an amplitude signal. Now, have you ever noticed when you're listening to a radio, to your 2-meter radio during a thunderstorm, if you listen to the racing stuff, do you ever hear static? You ever hear thunder crashes? On 2 meters FM, you don't hear thunder crashes. If you were listening to an AM radio on that frequency, you hear all the thunder crashes and lightning and everything. Why do you think that is? Because the limiter kept all that, those would all be spikes up above the top of the signal, those would be spikes. It keeps those spikes out. It limits out all that noise. So only what you're getting is the amplitude of the FM signal that's going in there. A limiter takes all that stuff out.
Kind of like the waveform you were showing.
Yeah.
Like the splatter,
Yeah.
but it doesn't splat. It just
Yeah.
goes on through.
Yeah, because it'll have those components in it. So it takes that, it can't help but have those components in it. but it's going to take that out. So limiter keeps that thing at a steady height, as far as the amplitude goes, a steady height FM signal. It goes into the thing that takes out everything and makes it audio, that strips out everything except the audio on an FM receiver is called a discriminator or quadrature detector. Hint, on your test, if you see a block diagram like that, and they say, what kind of radio is that? Look for that. If it says discriminator or audio detector, it's an FM radio. If it doesn't say that, it's going to be an AM or single sideband radio. It goes into the AF amp and on out to the speaker. It increases the gain of the signal. Local oscillator, remember what that did? Generate a low frequency signal, combines with the RF, filters out all but the intermediate frequency, clips the noise peaks, that's the thunder and stuff you hear, separates out the audio signal, amplifies the audio signal. We're ready for a review. Frequency modulation. It changes the instantaneous frequency of an RF wave to convey information. The change in frequency is what conveys information. And amplitude modulation changes the amplitude, the strength, to convey information. That's the difference between the two of them. Single sideband is AM with one sideband and the carrier suppressed. We talked about that last Tuesday. A single sideband is the narrowest bandwidth phone emission. The balance modulator combines voice carrier for a single sideband signal that feeds the filter select upper sideband and lower sideband. RF amplifiers, A, B, B, and C. A is the most linear but least effective. C is the most efficient but least linear. C is good for FM signals. Efficiency is the ratio of RF output over DC input. If you're on an RF amplifier, you adjust the load for maximum power output, and you adjust the plate meter for a pronounced dip. Dip the plate. At AC waveforms, the peak-to-peak waveform measurement includes positive and negative waveforms. That's peak to peak, two peaks. Not only peak to O peak, but you might say TWO peak if that helps you. Peak-to-peak waveform. Peak waveform is a measurement of half the peak-to-peak value. The DC equivalent of a peak value is 0.707. So if you're going to do a calculation that requires DC and they give you an AC, how much AC peak it is in it, then you just multiply times 707 before you go finish the calculation. It's known as the RMS value. Oscilloscope, nice tool, has two axes, horizontal for frequency, vertical for amplitude or strength. And if you're going to put RF into it, your radio frequency into it, you got to put an attenuator on to get it down to a measurable level. You can use it when you check the keying waveform of a CW or single sideband signal to see how pure it is. That's where we talked about chirps on your CW signal. You might not be able to tell if you have chirps, but if you put your signal, monitor your CW signal on an oscilloscope, you can actually see the chirps. You can see the extra stuff outside the waveform. I use a two-tone test for single sideband linearity. It's better than a voltmeter. You can not only measure strength like you do on a voltmeter, but you can also see what the waveform that you're measuring looks like. It may not be what you expect. You may think you're looking at DC and you may see a bunch of AC in there as well. They'll never show up on a meter. Speech processor, that's the guy that increases the average power and intelligibility of transmitted phone signals. An excessive level of processing, which is setting they might gain too high, can cause splatter, distorted speech. Excessive bandwidth, too wide a bandwidth might get you, if you're operating on the edge of the band, might get you outside of the band and picks up a lot of background noise. A mixer is one of those things that combines two frequencies to get other frequencies. You get the sum of the two frequencies, you get the difference between the two frequencies. So you get this, you've got lots of frequencies. You've got 4 frequencies when you mix 2 frequencies together. Mixing is also known as heterodyning. Heterodyning is when all of a sudden if you hear 2 waveforms on your receiver pretty close together and they kind of howl a little bit and squeal a little bit, That's actually those two waveforms mixing into one another on your receiver. That's called heterodyne. Mixing the received RF frequency with a variable local oscillator will produce the IF frequency. That's the one we on the front end of the radio. Yep.
The heterodyne there, you're not talking about it like if you're tuning in an AM signal in one of the side bands, are you?
Well, that's
That
what
line?
that line. That's a heterodyne as well.
Okay.
Yeah, you can heterodyne signals internally in your radio intentionally, but that's the effect of two overlapping signals on that you're receiving on your radio that's causing yet another frequency, and that's an audio frequency. Yeah. You can hear those frequencies. You can make those frequencies. You can heterodyne to make frequencies.